Hello everyone, now we will have a tutorial session and in this class we will solve some numerical problems based on our discussions in the last 4 classes. The first problem statement is find the flow rate of water in meter cube per meter square per day when it passes through a porous polythene membrane by a pressure differential at 70 degree centigrade. The membrane is of 20% porosity with 0.5 mm diameter pores and a tortuosity of 1.5. Pressures on either side of the membrane are 525 kilopascal and 100 kilopascal. Assume membrane is 2 micron thick and flow is fully developed laminar flow. At 70 degree centigrade, the viscosity and density of water is 0.00042 Pascal second and 1000 kg per meter cube. So, this is the statement and we have to find out the flow rate in meter cube per meter square per day, that means volumetric flow rate per cross sectional area per day, that is Q by A, that we have to determine this Q by A. So, this Q by A is equal to N by rho, that is the flux, the volumetric flux. So, mass flux divided by rho, so that is N by rho, and in the previous class we have discussed that N is equal to rho into E into d square into PO minus PLM divided by 32 mu Lm tau. So, that expression we have discussed. Now, N by rho will be, this is rho, N by rho, that is equal to these expressions we have discussed in the previous class, where this E or epsilon, this is your porosity, d is the diameter of the pore, PO is the pressure of one side and this is PLM other side pressure, and 32 and then mu the viscosity of the water, Lm is the thickness of the membrane layer and tau is the tortuosity. So, that we have discussed in the previous class. So, here the values are given. So, using those values we will be calculating this term, that is V is equal to N by rho or that is equal to Q by A. So, in this case mu is equal to given 0.0042 Pascal second, rho is given 1000 kg per meter cube and then PO 525 kilopascal, that is 525,000 Pascal, and then PLM other side pressure, that is 100 kPa. So, that is this one Pascal in Pascal, and epsilon is 0.2, that is porosity given, and diameter is equal to 0.5 micrometer, diameter of the pore. So, that is equal to 5 into 10 to the minus 6 meter. This will be 10 to the power minus 7, not 6. So, d equal to 0.5 micrometer, that is 5 into 10 to the minus 7 meter, and Lm is equal to 2 into 10 to the minus 6 meter. It is given the 2 micrometer thickness. So, that is 2 into 10 to the minus 6 meter and tau is equal to 1.5, it is given. So, we will be using this V equal to E d square into, we are giving P0 minus PLM divided by 32 into mu into this Lm into tau. This term we are getting from the previous expression, but here another 2 term is there 3600 into 24, because in the previous expression, in this expression that which we have discussed, that is V equal to Q by A. So, that is Q by A. So, that Q was in the unit of Q was meter cube per second. So, we have to convert it into per day. So, that 3600 into 24 is multiplied, and then after getting the solution of this expression, the V is coming as 45536 meter cube per meter square per day. So, we are asked to calculate this one and now we are able to solve it. Now, we will see problem number 2. Statement is each 100 ml solution containing 20 mg per liter fluoride is treated with 2 different adsorbent doses that is 6 gram per liter and 4 gram per liter separately. The percentage removals of the fluoride for these two cases are 60% and 50% respectively. Calculate the specific uptake for both the cases and explain the trend. So, we have to calculate the specific uptake of the adsorbent which is used to remove the fluoride from the water. Two different cases are given and their adsorbent dose is different, initial concentration is different and removal of the fluoride is also different. Okay. So, we will be calculating the specific uptake, then specific uptake we know that the amount of adsorbate taken up by unit mass of the adsorbent. So, here for case 1 initial concentration of fluoride is equal to 20 mg per liter. So, final concentration of F will be how much? 60% is removed. So, 20 into 1 minus 0.6 60%. So, 0.6 1 minus 0.6. So, 0.4 into 20 that is equal to 8 mg per liter. So, this is our final concentration. So, adsorbent. So, this is our final concentration. Now, adsorbent used is equal to how much? 6 gram per liter, but we have 100 ml solution. So, we are using 6 into 100 divided by 1000 that is 0.6 gram, and what is the amount of adsorbate or fluoride taken up by this 0.6 gram of adsorbent, that we can calculate by this way, that fluoride removed by the adsorbent initially 20 we had, now we are having 8. So, 20 minus 8 that is 12 mg per liter, but we have 100 ml not 1 liter. So, into 100 divided by 1000. So, that is 20 minus 8 divided by 1000 into 100. So, that is equal to 1.2 mg. So, 1.2 mg fluoride is taken up by 0.6 gram of the adsorbent. So, specific uptake is 1.2 mg divided by 0.6 gram, that is 2 mg per gram. So, that is 2 mg per gram we are getting in this case as the specific uptake. So, for case 1, but for case 2 what we will get? The initial concentration of fluoride is again 20 mg per liter and final concentration will be 20 into 1 minus 0.5 that is 50% removed. So, remaining is 50%. So, 0.5. So, that is equal to 10 mg per liter, and adsorbent used equal to how much? 4 gram per liter. So, 4 divided by 1000 into 100. So, that is 0.4 gram, and fluoride removed by the adsorbent that is equal to 20 initial and finally available 10. So, removed is 20 minus 10 and that is taken up by the adsorbent. So, this is divided by 1000 into 100 that is equal to 1 mg. So, 1 mg fluoride is taken up by 0.4 gram of adsorbent. So, what is the specific uptake? Here 1 divided by 0.4 that is equal to 2.5 mg per gram. So, the second case specific uptake is 2.5 mg per gram, but in the first case the specific uptake is 2 mg per gram. So, you see in this case with the increase of initial concentration we are getting lesser percentage removal, however, we are getting more specific uptake. This is apparently in opposite trend. With the decrease in adsorbent dose, the adsorbent is getting more available adsorbate molecules and capturing more adsorbate. So, that is why specific uptake is being increased with the decrease of adsorbent dose, but percentage removal is not giving the same trend, because percentage removal is the factor final and initial concentration. Thus, this is not giving the same trend with respect to specific uptake. So, the trend of specific uptake and percentage removal is not similar, it is opposite. Okay. Now, we are coming to problem number 3. Statement is a 10 centimeter diameter column is packed with adsorbent to a bed height of 1 meter. A liquid with a density of 1000 kg per meter cube containing 0.5% adsorbate is delivered at a flow rate of 5 bed volume per hour. The breakthrough versus time curve is approximately S shaped. Adsorbate is first detected in effluent after 10 hours and the concentration reaches that of the feed in 11 hour. Calculate the following: the capacity of the adsorbent at breakthrough, the full equilibrium capacity and the length of the unused bed. So, this is again a problem of the adsorption in packed bed column, packed column. So, your height is given, okay, liquid density given, the solid content is given and its flow rate is also given. So, we have to calculate these parameters. So, we will be using the mass balance. So, now let us see the bed volume. What is the bed volume? So, that is equal to pi r square into h. So, that is pi r square h or pi d square by 4 into h. H is the height and then pi by 4 into d square. In this case the d is equal to 10 centimeter. So, in terms of meter it will be 0.1. So, pi into 0.1 square by 4 into 1 meter is the length. So, that is equal to 0.0079 meter cube. Then the flow rate is 5 bed volume per hour. This is our bed volume. So, 5 into this 0.005, 5 into 0.0079. So, that is equal to 0.0395 meter cube per hour. So, now we are getting the flow rate. So, then adsorbed feed rate is equal to how much then? What is our flow rate? We are getting that is in volume. Then we will convert it into mass. So, 1000 kg per meter cube it is given and it is given that 0.5% solid is present. So, this is the total mass of the influent. So, adsorbed feed will be this into 0.5%. So, that is multiplied by 0.005. So, that we are getting 0.1975 kg per hour. So, this much of adsorbate is passing through the adsorbent bed and being captured by the adsorbent. Then the adsorbent capacity at breakthrough, what will be our adsorbent capacity? This is our adsorbate which is captured by the adsorbent. The volume of that adsorbent is the reactor volume 0.0079 and 0.1975 into 10 which we have calculated here. So, we have 10 hour, first time we are getting the concentration of the pollutants at the outlet from the packed bed. So, that is 10 hour time, 10 hour into this kg per hour. So, this is the total adsorbent captured by the adsorbent bed, that divided by the volume of the adsorbent available in the bed. So, that kg per meter cube we are getting 250 kg per meter cube. If we have the density of the material adsorbent, then we can get the that we can convert it into kg per kg, okay, or mg per kg. So, that way we will be able to get the specific uptake, and here we are asked to adsorbent capacity at breakthrough is like this. This is adsorbent, we can say, not adsorbate, capacity at breakthrough is this much. Then second part is the full equilibrium capacity. Here after 10 hour, the first detected in effluent after 10 hour, adsorbate is first detected in effluent after 10 hours. So, capacity of the adsorbent at breakthrough, this is our breakthrough, and concentration reaches that of the feed in 11 hour. So, 11 hour concentration reaches. So, we will be having this type of graph, the SF. So, this is our and this is our. So, we will be taking this, this is our 10 and this is our 11. So, this will be half of that. So, 10.5. So, 10.5 hour we will be considering this time is taken to completely exhaust the bed. So, the same method we will be using, but we will be using as 10.5 hour to calculate the adsorbate adsorbed on the adsorbent. So, same formula we will be using, and in that case T will be not 10 hour, it will be 10.5 hour. So, the specific uptake or the adsorbent uptake capacity, that will be 250 which we have into 10.5 divided by 10. So, that is equal to 262.5 kg per meter cube, that will be getting. Then third part, length of unused bed we have to used. So, in that case, in our previous class we have discussed one formula, that is LUB is ideal wave front velocity into T s minus T b, and that is equal to LE by T s into T s minus T b. So, the same graph if we plot like this. So, this is our T s, okay, and this is our half of it will be getting T s. So, which T s we have mentioned here, that is mentioned here as T star. Okay. So, this T s and T star is same. So, in that case we have seen that LUB is equal to LE into T s minus T b by T s, that is T s is T star. So, LE into 1 minus T b by T star. So, this is the formula we have used in our previous class to calculate the LUB value. So, in this case LE is equal to 1 meter and T b and T star. What is T b? T b is taking this one, this is our T e and this is our T b. Okay. So, this is T b and this is T e. So, 1 minus 10 divided by 10.5. So, this formula we are getting 0.048 meter, 0.048 meter. Okay. So, this is the LUB, that is not, that bed will not be used basically. Then problem 4, 1 lakhs liter per day of liquid containing 0.1% adsorbate is to be treated. During pilot plant testing of adsorbent, performance was investigated at a superficial velocity of 0.03 meter per second with total tolerable pressure drop and adsorption capacity of 0.3 kg adsorbate per kg adsorbent. The feed density is 1000 kg per meter cube, the adsorbent bulk density is 640 kg per meter cube and the desired online time is 48 hours. And then determine column diameter and packed height. So, again adsorption based problem, we have to determine the column diameter and packed height. So, certainly in that case we will be using the mass balance. So, the volumetric flow rate in meter cube per second, if we want to calculate, we have 1 lakhs liter per day. So, 1 lakhs divided by this 86400 second. So, that is conversion second to day, and then this is meter cube liter per day, we are interested to convert it into meter cube. So, again we have to divide it by 1000. So, these divisions are done basically to convert the unit. So, that liter per day to now we are getting meter cube per second, that is 0.00116 meter cube per second. The required cross sectional area A is equal to volumetric flow rate by superficial velocity. So, this is our volumetric flow rate and superficial velocity that we know, and in this case what is this? It is given that superficial velocity 0.03 meter per second. So, that we are dividing, so that it is coming 0.386 meter square. So, this is the cross sectional area. So, if it is the cross sectional area, then what will be the diameter? Again cross sectional area A equal to pi d square by 4. So, d equal to 4 into A by pi root of it. So, this formula we are getting. So, this 4 into A equal to we have getting here, this value will put, and by pi. So, by solving this expression, diameter equal to 0.7 meter. So, diameter we are getting. Now, we have to determine the height also. Then how we will do? The amount of adsorbate delivered to the column per cycle we will calculate. So, we have 48 hour period and we have 10 lakhs liter per day. So, divided by 24 and multiplied by 48. So, we will be getting now how much liter of water is treated. So, that converted into meter cube by dividing it by 1000, and then we are converting from volume to mass. So, we are multiplying it with the density, that is 1000 kg per meter cube, that is the amount of adsorbate delivered to the column per day. this is the mass of the total inlet, but we have to calculate the amount of adsorbate delivered. So, what is that? What is the percentage it is given? It is given that, what is that? It is the percentage of adsorbate it is given, that is 0.1%. So, we have multiplied this 0.001. So, this value is coming as 200 kg. So, this 200 kg is the amount of adsorbate delivered to the column per cycle. So, what will be the adsorbent needed? So, adsorbent needed is equal to 200 kg divided by 0.03, because kg adsorbent by kg adsorbate it is given, and 640 kg. So, this much of adsorbent is required, then we are dividing it by the density of the adsorbent. So, we are getting the volume of the adsorbent. So, once we are getting the volume of the adsorbent, that means it is the volume of the packed bed, and then height will be volume by area. So, volume we are getting 1.04 meter cube, and area we have got 0.386. So, that height is equal to 2.7 meter. So, that way you can calculate. Next, problem number 5, the statement is, consider a fixed bed adsorption before breakthrough in which L ideal by L b is equal to 0.5, take Q equal to 1 liter per second, T ideal equal to 100 second, the mass of the adsorbent used equals to 100 gram and inlet concentration of 20 kg per meter cube. Adsorption follows the Freundlich adsorption isotherm with Q equal to 5 into C to the power 1 by n. Calculate the mass of adsorbent required for the inlet concentration of 25 kg per meter cube. So, it is again a problem of adsorption based process. So, we have a fixed bed, L ideal by L b total length it is given, okay. Flow rate is given, T ideal is given, and mass of the adsorbent used is also given, and initial concentration is given, and the specific uptake how to calculate, that formula is also given. So, by doing the mass balance we can calculate the value of n, that is the Freundlich isotherm constant for the first case, and the second case we will be using that n value to calculate the Q, and then we will be doing the mass balance and we will get the desired values, the mass adsorbent required for the inlet concentration of 25 kg per meter cube. Okay. So, this way we will proceed. Now, say material balance of the adsorbate before breakthrough occurs, that we know in our previous class we have discussed, that is solute in entering feed equal to adsorbate adsorbed on the adsorbent. So, what was the solute in the incoming feed? We have volumetric flow rate, we have time, and we have concentration of it. So, Q into C into T ideal is the solute entering into the bed, and the solute or the adsorbate captured on the adsorbent, that will be Q into S. Q is the specific uptake and S is the adsorbent present in the adsorbent bed. Here L ideal by L b, because like this, if it is a ideal, so up to this, say from initial T equal to 0, and here say this will be ultimate, this part is adsorbed, okay. So, this is L ideal and this is your L b, okay. So, if total S is present in it, material total material S, so material present in this part will be S into L ideal divided by L b, okay. So, that is the material total term. So, this term is the material present in this multiplied by Q specific uptake. So, that is the adsorbate captured by this material, okay, and that amount of adsorbate has entered into this bed, that is Q C T ideal, okay. And this Q value we can calculate by this 5 into C to the power 1 by n, In this case Q value is given 1 liter per second, that is equal to 0.001 meter cube per second, and C equal to 20 kg per meter cube, and T ideal 100 second. S equal to 100 gram, so that is equal to 0.1 kg for the total, okay, and L ideal by LLB, that term is given is equal to 0.5. So, we will be putting all those values in this expression and we will get the value of N. So, Q is equal to Q into C into T ideal by S into L ideal by LB. Q is equal to 0.001 we have calculated, C is equal to 20, and then this is T ideal 100, and here we are getting S is equal to 0.1 and L ideal by LB is equal to 0.5. So, by this we are getting Q is equal to 20 kg per kg adsorbent. So, 20 kg adsorbate by kg adsorbent. So, the first case we are getting the value of Q. So, for the second case we will be using this Q value, because the Q value will be remaining same, the maximum specific uptake that which is determined from the Freundlich isotherm, that will be same for both the cases. So, Q is equal to 5 into C to the power 1 by n. So, that value we are calculating now, the what is the value of n. So, 40. So, now we will put this Q value in this expression and we will get the value of n. So, 40 equal to 5 into 20 to the power 1 by n, or 8 equal to 20 to the power 1 by n, then we will take log. So, log 8 equal to 1 by n to log 20. So, n is equal 1 by n is equal to log 8 by log 20. So, that n is equal to 1.44. Okay. So, for C equal to 25 kg per meter cube and assuming all conditions same, the weight of the adsorbent needed is, we will be calculating here, that is this much. Q C T ideal will be our amount of adsorbate getting entry into the packed bed, and this is the formula which is used to calculate the adsorbed material, that is adsorbent on the adsorbent, adsorbate on the adsorbent. So, S is equal to Q into C into T ideal by Q into L ideal by LB. Now, what is the Q in this case? Q is equal to 5 into 25 to the power 1 by n. So, 1.44. So, that is equal to 46.74 kg per meter cube. So, this value we will be putting here for S, the Q value is given, C value in this case is different. So, that is 0, that is 25 kg per meter cube. So, 25 into 100 T ideal divided by this Q value 46.74 into 0.5, that is equal to, this is remaining same, L ideal by LB. So, we are getting that 106.97 gram. So, the S value in this case will be 106.97 gram. So, this much of adsorbent will be required. So, up to this in this class, thank you very much for your patience.